Today, we're going to look at the graphs of sine and cosine and start to make connections between the graphs that we see and the equations that we use to describe those graphs, so that we can look at an equation and figure out what the graph looks like, or look at a graph and figure out what an equation looks like. Note that when we're talking about the graph, we could also be talking about a set of data, because graph is just a visual representation of a bunch of points. So if we have a bunch of points that we suspect to be sinusoidal, we could look for these characteristics and come up with an equation based on that numerical information. So I'm going to name some parts on one cycle of the sine and cosine, some parts that they have in common, and how I'm going to refer to these graphs. Since the sine and cosine are going to be coordinates going around a unit circle, we're going to be constrained between 1 and -1, because the circle is all the points that are 1 unit away from the origin. So the x and y coordinates can never be more than 1 unit away. We'll have to do something to sine and cosine to get further than 1 unit away from the origin. I'm going to refer to, on these graphs, a top, a middle, and a bottom. So there's going to be a top, a middle, and a bottom. So there's going to be a top, a middle, and a bottom. The default for the top will be at 1. The default middle will be 0, and the default bottom will be -1. So we have a top, a middle, and the bottom. The default values are going to be 0, 1, and -1. We're going to refer to the distance from the middle to the top or from the middle to the bottom as the amplitude. So our default amplitude is equal to 1. So the amplitude is the distance from the middle to the top or the middle to the bottom. So the bottom is at -1, but the distance from the middle to the bottom is going to be 1. Our amplitude is going to be a positive number. So amplitude is the distance from the middle to the top and it should be the same as the distance from the middle to the bottom. So I've got a top, I've named the top, a middle, and a bottom, and the distance is going to be the amplitude. We're going to have to find a way to change the amplitude, to change the distance from the middle to the top and the middle to the bottom. We're going to have to find a way to change where the middle is. If I change one, then change them all. So we're going to have to figure out how to move the middle up and down, and we're going to have to figure out how to increase the distance, increase or decrease the distance from the middle to the top or the middle to the bottom. Now, these graphs go on forever for left and right. This is just, each of these pictures is just one cycle of each of these functions. Either way, I'm going to refer to 5 important points horizontally. I'm going to refer to this point on sine as the start, and I'm going to put it in quotes so that we recognize that there's no beginning and no end. And so the cosine, I'm going to refer to this as the start And once again, I put it in quotes because there's no beginning, no end. It goes on forever both ways, but this is like the start of one cycle. I'm going to name the 4 places on the graph. So I'll say that cosine starts at the top, and then it goes to the middle, to the bottom, to the middle, and then to the top. Notice that the sine starts off at the middle and then goes to the top. So the way I phrase this, I say that sine theta, sine starts at the middle going up. So I refer to where sine starts as the middle going up. And then the other midpoint in the middle is going to be the middle going down. So we'd say sine starts at the middle going up, then it goes to the top, then to the middle going down, then to the bottom. And then it just repeats those 4. Cosine starts at the top, then goes to the middle going down, then to the bottom, then it hits the middle going up, and then it's back at the top. And we're just going to cycle through those 4. The middle going up, the top, the middle going down, the bottom, the middle going up, the top, the middle going down, the bottom, the middle going up, and so on. We're just going to cycle between those 4 wherever we actually think about starting. So it's going to be the mid, I'm just going to use the sine, the mid going up, and then to the top, then the mid going down, then the bottom, then the mid going up, because trig functions have this periodic behavior. And so these are the points. These are just local descriptions of these points. If you look on YouTube and ask how does the middle going down thing work, you won't find it unless I put it in the description. But these are how I refer to these points. There's the middle going down, there's the top, there's the bottom, then the middle going up, then the top. And so I'll say things like sine starts at the middle going up. Cosine starts at the top. Any questions? When we get back to the point that we started, so if we start off at the middle going up, we go to the top, the middle going down, hit the bottom, and we're back at the middle going up. That's going to be the length of one cycle, and we call that the period. So each of these is one cycle. So here the sine starts at middle going up. They go to the top, the middle going down, the bottom. We're back at the middle going up. This is one cycle, and this is the length of one period. For cosine, we start at the top, hit the middle going down, hit the bottom, the middle going up, back at the top, that is one period. I spelled P wrong. The default period for sine and cosine is going around the circle one time, and so the default period is going to be 2 pi. Sine theta and cosine theta both have a period of 2 pi. The important parts, the middle going up, the top, the middle going down, and the bottom, those happen at quarter multiples, or at quarters of the period. So if we start off at the mid going up, we hit the top at 1/4 period. We hit the middle going down at a 1/2 period. We hit the bottom at 3/4 of period. And then we hit the middle going up where we started at 1 period. So all these points, the middle going up, the top, the middle going down, and the bottom are all 1/4 period apart. This is the information that we're going to need to figure out what the equation should look like given a graph, or what the graph should look like given an equation. Any questions? So this first part is just the naming of the parts. These are the words that I'm going to use to describe what's going on in the graph. We got the amplitude, we got the period, and then we got the local wording where I talk about the middle going up, the top, the middle going down, and the bottom. In the two graphs we see here, we see that sine starts at the middle going up and cosine starts at the top. How's everybody okay so far? I remember a poem from high school called The Naming of Parts. I don't know why that stuck with me so much. How weird. Then again, since I'm remembering it, there's no way to know if that's actually true or not. That might just be an implanted memory, because human memory is really weird. If you don't remember something and someone knows that, they can convince you you remember something that actually didn't happen. And you could be 100% convinced that something that didn't happen totally did happen. We're very susceptible to suggestion. And if we find gaps in the story that we're trying to tell and someone asks about them, we fill in those gaps, whether we remember them or not. And when we fill in those gaps, we are making stuff up. But we're convinced that it's true. You can put us on a lie detector and we'll be absolutely convinced that we are right. What are we talking about? Ah, yes. This is just the naming of parts and our default values. We'll have a default amplitude of 1, a default middle of 0, a default period of 2 pi, and a default start of theta equals 0. I didn't label that. Our default start is theta equals 0. So you can see, I'm going to want to be able to stretch these up and down, change the amplitude by making the bigger distance from the middle to the top. I'm going to want to move the middle up and down, thus moving the top and the bottom by the same amount. And I'm going to want to do the same thing horizontally. I'm going to want to change the period, make the period shorter or longer. And then I'm going to want to shift the graph left and right, change the start left and right. I'm going to want to shift the graph, and I'm going to want to stretch the graph horizontally and vertically. So the things that we're going to want to do . So we want to make the following alterations. We want to stretch or squish. We want to stretch. Or we want to shift. We're going to want to do this horizontally . And we're going to want to do this vertically. When we stretch things, we're going to change the amplitude or the period. So the things that we're going to change with the stretch are the amplitude and the period. Things that we're going to change with a shift is going to be the middle or the start. We're going to want to change things horizontally. Horizontal information is the start and the period. We're going to want to change things vertically, which means we're going to want to change the middle or the amplitude. So we're going to make horizontal changes or vertical changes. We're going to make stretches or we're going to make shifts. Notice that we got these 4 possibilities. A horizontal stretch is going to alter the period. That's what we have in common here. A horizontal stretch will alter the period. A vertical stretch will alter the amplitude. A horizontal shift will alter where the graph starts. I should put that in quotes. And a vertical shift will change where the middle goes. We're going to make these changes with operations. We're going to make these changes with operations. These operations are going to happen before we apply the trig function or after we apply the trig function. So let's jump over to Desmos and start messing with some things. Let me make sure I have Desmos up. I do. All right. I usually don't, so there's like this big pause where I have to start typing stuff in. So let me switch over to Desmos. Let's all check out. Let's do some experimentation. So what I have here is the graph of A times the sine of BX. And I set up sliders so I can adjust the value of A or adjust the value of B. I don't really need -10 to 10. Let's go like from -3 to 3 with a step size of just 1. And let's change B to go from -4 to 4 with a step size of 1. Now I want to change this one to match it. 4 is not lucky, and I'm going to have to go with it anyway. I've already done enough on that. All right, so let's take a look at A sine of BX. Now, A is being multiplied by the sine of BX. So the multiplication by A happens after the trig function. And multiplication by B happens before the trig function. So in both cases with A and B, I'm altering the equation with multiplication. In one case, for one value, I'm multiplying before the trig function. The other one I'm multiplying after the trig function. Let's see what happens when we change the value of a, multiplication after the trig function. What I mean by after the trig function, I mean, if we plug a value of x in, the first thing that happens is we multiply by b. The next thing that happens is we take the sine of what we get. And then third thing that happens is we multiply by a. So let's watch what happens when I change the values of multiplying and multiply by a. So here I got the top, I got the middle is at 0, the top is at 1, and the bottom is at -1. So there are our 5 points in one cycle. If I change the value of a to 2, notice that all that's changed, my horizontal values did not change, the middle did not change, but the vertical, the amplitude has changed to 2. The distance from the middle to the top is now 2. Top's at 2, bottom's at -2. When I change the value of a to 3, the top's at 3, the bottom's at -3, the middle is where it was, and the period is still 2 pi. Same thing with 4, it just stretches it vertically. 3, 2, 1. If I multiply by 0, that flattens everything out. So if I do multiplication after the trig function, I stretch the graph vertically. So I'm making vertical changes to what's going on. I can make it go fast. Be like Knight Rider talking to you. Hello, Michael. Where are we driving today? I don't know if any of you are old enough to have seen Knight Rider, but there it is. So multiplication after the trig function changed the amplitude. The middle stayed where it was. I didn't shift it anywhere. I just stretched it. Now, if I make a go less than 1, so if I drop a down below, notice that if a is 0.6, then the top and the bottom are at 0.6 and -0.6. The period is still 2 pi, the middle is still at 0. So we've stretched it, but flattened it, so it's kind of a squish. Any questions? David Hasselhoff is huge in Germany. It's almost baffling. I don't know if it's true, but I heard he bought the rights to Baywatch for like 50 grand or something like that. Because the networks are like, oh, no, we don't want to watch this. We don't want this show. This is dumb. And David Hasselhoff says, can I buy it for like 50 grand? And they're like, oh, sure. And then it became like the biggest television show in the world. So crazy. Multiplication after the trig function produced a vertical stretch. Multiplication after the trig function produced a vertical stretch. The same thing happens in cosine. So notice that if I start stretching out cosine, I'm just stretching the graph vertically or squishing it vertically. Let's change another value. I want to put this at 2 so it shows up a little better. Here's our cosine. Middle is still where it should be. The period is still at 0. The period is still 2 pi. The amplitude has changed to 2. Let's start messing with multiplication before the trig function. That's values of b. So if the value of b is equal to 1, I see we have a period of 2 pi. But if I change the value of b to 2, notice that one cycle is happening much faster. Now we're back on cosine, we're back at the top at pi. So one cycle is now dropped down to pi. The amplitude didn't change, the middle didn't change, and the start didn't change. Same thing on, oh, it's gonna get. Very messy if I try to put it all on there. But here are the 5 points of one cycle of sine. The start is still at 0, the period is dropped down to pi, but the middle is still 0 and the amplitude is still 2. If I increase the b to a 3, now the period is even shorter. Notice that the period has dropped down to 2 pi over 3. From the middle to going up to the next middle going up, that period is now 2 pi over 3. Same thing on cosine. The top is it starts at the top 2, hits the bottom at pi over 3, and it's back to the top again at 2 pi over 3. So when b is equal to 3, the period is 2 pi over 3. And if I increase b to 4, then we can see that the period has decreased further still. Now when b is equal to 4, the period's all the way down to pi over 2. So notice what's happening. The middle is staying where it is. The start is staying where it is. For all these different values of b, the start is still at 0. Cosine is starting at the top at 0, 2. Sine is starting at the middle at 0, 0. But multiplication before the trig function is causing a horizontal stretch. When b increases, we squish it. When b decreases, we start stretching the graph. So that when b drops down to say 1/2, one cycle now takes longer. Top, middle going down, bottom, middle going up. Back to the top, the period is 4 pi. So multiplication before the trig function is producing a horizontal stretch. Multiplication after the trig function produced a vertical stretch. So the vertical, so going back to the chart, our vertical stretch, which adjusted only the amplitude, was multiplication after the trig function. So this amplitude was changed with multiplication after the trig function. So we had multiplication after. We adjusted the period by applying multiplication before the trig function. What changing the amplitude and changing the period had in common was the multiplication. Multiplication produces a stretch. It's multiplication that's producing a stretch. Any questions? Let's go back and switch to addition. We're going to trade our multiplication for addition, and you can probably guess what's going to go here. So let's switch over back over to the Desmos. Go back to our default graphs. Now let's look at a new paragraph. Let's say y is equal to, I'm going to set up a function where I have sine and cosine, and I'm going to have addition before the trig function and addition after the trig function. So let's set that up. I'm going to have sine of, say, x. I guess I'll use c. minus C plus D. Sliders for all. And then I'll set up another function. I forgot to do these clearly beforehand. The cosine of the same thing, x minus C plus D. Keep this up here. Turn off my A and B's. I got sliders for C and D now. Our default values of C and D are 0, but we can see what's going to happen because I started moving them already. Here, if I highlight the orange one, that's cosine. Our amplitude is 1, and our period is 2 pi. Now I'm going to start moving the values of C back and forth. So if I start moving the values of C, notice that we're maintaining the same amplitude and the same period, and we're maintaining the same middle. When we do addition or subtraction before the trig function, we end up with a horizontal shift. So you can guess what's going to happen if I start moving the values of D up and down. When I start moving the values of D, the middle is what's changing. The amplitude is not changing because the graph is not stretching, and the period is not changing. It's the middle that changes. So when we perform addition after the trig function, we get a vertical shift. When we perform addition before the trig function, we get a horizontal shift. So we go back to our chart. Adjusting the middle is when we performed addition after the trig function. And when we adjusted the start, when we shifted horizontally, we were doing addition before. So what the shifts have in common is the operation of addition. We get vertical changes when the operation happens after the trig function, and we get horizontal changes when the operation happens before the trig function. So horizontal changes are operations before. Vertical changes are operations after. So we need to worry about the operation, multiplication or addition, and the timing, before or after. Now all we have to do is translate all this into what we see in a graph and connect that to an equation. But these are the four things that we're going to be doing. I want you to think of stretches versus shift. I want you to think vertical versus horizontal. I want you to associate multiplication with stretches and addition with shifts. I want stuff before the trig function you to associate before the trig function with horizontal, after the trig function with vertical. So this is how we keep things organized. The other reason that I want to think about it in these terms is that these terms, the way of these, thinking about stretching and shifting in this fashion translates to functions in general, not just trig functions. Words like amplitude, period, start, middle, that's all specific to sine and cosine. But vertical and horizontal, stretches and shifts, that works for all kinds of functions. I especially want to associate multiplication with stretching and addition with shifting, and after with vertical and before with horizontal. Because then we'll be able to branch out to more complicated or operations more complicated than multiplication and addition. Any questions? Comments? Deep thoughts? So let's write down an equation with a bunch of different changes and figure out the 4 things that we need to figure out: the middle, the amplitude, the period, and the start. Then we can draw a graph and figure out what the equation should look like. So make sure you get a picture of this. We're going to use this and find these 4 things about the graph. Also make sure that you have this picture in your mind. I mean, you've seen the chart and the graphs one time, so that should be plenty. I know you're all experts in graphing sinusoidal functions now. Oh wait, I just got through saying that's not how memory works. So you might have to refer to the notes. Heck, I might have to refer to the notes. Who knows what I remember? So let's look at an example. So we're gonna write a function and we're gonna want to identify the middle, the amplitude, the start, and the period. And we're going to do this by identifying whether an operation happens, that an operation is addition or multiplication, and whether it happens before the trig function or after the trig function. Let's write down a function. Let's say y, or write down an equation. Let's say y is equal to 5 times the cosine of 4 theta plus 3. I don't know why it took me so long to write that. I already knew I was going to use 5, 4, and 3. And I knew I was going to skip changing the start. Let's think of the function 5 cosine of 4 theta plus 3. Let's think about what each of these numbers do, and then use that information to figure out what the graph should look like. Oh, we should also remind ourselves of our default. Our default start is that theta is equal to 0. Our default period is equal to 2 pi. Our default amplitude is equal to 1. And the default middle is equal to 0. Now, putting numbers, putting operations, multiplication and addition before and after the trig function could change these default values. We've got to start somewhere. Let's look at the equation and see what each of these numbers does. I have 5 in front of a cosine of 4 theta plus 3. Let's think about what happens to the theta. So start at theta. The first thing that happens is we multiply by 4. This 4 is multiplication before the trig function. So theta gets multiplied by 4, then we apply the cosine. Once we have the cosine of 4 theta, then we multiply the result by 5, and finally, we add 3. So let's make a list of the order of operations that have happened. So we start with theta. The first operation that happens to theta is that we multiply by 4. After we multiply by 4, we apply the cosine. So the second thing that happens is we do the cosine of whatever we got. After we do the cosine, we multiply by 5. And finally, we add 3. We're just following the order of operations, not the PEMDAS order of operations, because PEMDAS is trash. We're just reading what is happening in this function and listing the things that we need to do to theta. First multiply by 4, then find the cosine of the result, then multiply by 5, then add 3. So we can see here in step 2, this is where the trig function has happened. So that 4 represents multiplication before the trig function. So the times 4 is multiplication before the trig function. It's multiplication. And it's happening before the trig function. And so that 4 is going to change, is going to produce a stretch or a squish, a stretch horizontally. Horizontal stretch. So that times 4 is going to change the period. Then cosine happens. That 5 is multiplication after the trig function. Since it takes place after, that's going to be multiplication after is going to be a vertical stretch. And that's a change in the amplitude. So that 5 is going to change the amplitude. Then the other thing is the plus 3. 3 is addition. The plus 3 is addition. And this is taking place after the trig function. So that means that plus 3 represents a vertical shift. Vertical because after, shift because it's addition. So the plus 3 is going to be a vertical shift that will change the middle. Normally the middle is 0, but we've changed that to 3. Normally the amplitude is 1, we have changed that to 5. Normally the period is 2 pi, but we're going 4 times as fast. So the period is going to be pi over 2. That's what we saw in our graph. So if we jump back over to the graph, if I change the value of b to 4, let's drop these down to 0. If I change the value of b to 4, oh, I turned those graphs on. Heck. If I change the value of b to 4, then the period is now pi over 2. Here's how we're going to think about it. Since we're looking at the cosine of 4 pi, think of it as going around the circle 4 times as fast. When theta is at 30, 4 theta is at 120. we're going around the circle 4 times as fast. So the period is not going to go all the way out to 2 pi. The period is going to be 2 pi divided by 4. So the period is 2 pi divided by 4, or pi over 2. Notice that if I change the amplitude, I didn't go all the way out to 5. I zoom out. But when the amplitude was 4, or if I change it to 5, when the amplitude, that just multiplies by our default amplitude. So since we have a 5, everything is being multiplied by 5, the amplitude is equal to 5. We just multiplied the default amplitude by 5. The 3 is changing the middle. So if I add a vertical, notice that when D is positive, the graph goes up, and when D is negative, the graph goes down. So the default is 0. And if I have a +3 at the end, that shifts the graph up 3 units. And so the middle, the default is 0, and we do +3. So it's weird that when we changed the period, we divided by 4, even though the equation says multiply by 4. But the way we're going to think about this is that we're going around the circle 4 times as fast. Notice that times 5 after and +3 after, we just multiplied the amplitude by 5 and added 3 to the middle. Took the default values and did exactly what the operation was. But when the operation happened before the trig function, it's kind of like we did the inverse. Instead of multiplying the period by 4, we divided the period by 4. So if I wanted to graph this function, I would start with the middle at 3. I would have an amplitude of 5. So now I can see where the top and the bottom are. So that means the top will be at 8, and the bottom will be at 3 minus 5, -2. So now I know the top, the middle, and the bottom. I didn't change anything about the start value, so the default start is at 0. So we're going to start here on the vertical axis, where theta is equal to 0. And the period is pi over 2. And I'm going to divide the period in quarters, because that's once around the circle. So I had to go, I cut that in half. Oops. 1, 2, 3. Oops. Approximate it. I lost track of my grid. So 1/2 of the period 1/2 the period will happen at pi over 4. Then I'll cut that in half again to a 1/4 period. If I cut a fraction in half, I make the denominator twice as big, so pi over 8. And then I got a 3/4 of a period. Oops. 3/4 of the period will be 3 pi divided by 8. Just take your 1/4 period and multiply it by 3. Put a 3 in the numerator. So I've got where I'm going to have the top, the middle, and the bottom. Since it's cosine, I know cosine starts at the top. So I'm going to start the graph at the top, go to the middle going down to the bottom, to the middle going up, and back to the top. Remember that our halfway values, so middle is at 3, the top is at 8, halfway between will happen at the 60-degree reference angles, and that's how we can make sure that we have this bent the right way. It's going to be flat at the top, and down through the middle going down, flatten out at the bottom, bend it to hit the middle going up, and then bend it again so that it's flat when we get to the top again. We're using the fact that cosine of 60 is a half. So 1/3 of the way between 0 and pi over 8 is where we're going to hit halfway. Any questions? This seems like a lot to remember, only because it's a lot to remember, and you have to remember all of it all the time in perfect detail. And I did 2 sections in kind of an unusual way. This is my way of the way I read functions. This is section 4.1 and 4.2, but I'm going after it in the way that I read functions. And I really like to organize things like in this chart down here. I want multiplication to go with stretches, addition to go with shifts. I want things that happen before the trig function to be horizontal changes, and I want things that operations after the trig function to be vertical changes. The reason that I always start this way and the reason that I organize it this way, because I don't want this knowledge to be specific and just contained in trig functions. It's just the first real good opportunity we've had to look at changes, operation changes, and the effects they have on the function. Oh, the 8 and the -2 came from the fact that I knew the middle was at 3. We figured out the middle needed to be at 3, and the amplitude was going to be 5. So if we start off at the middle of 3, the distance to the top is 5. That'll put us at 8. So 3 plus 5 is 8. And 3 minus 5 will give us the -2. So I want the distance from the middle to the top and the middle to the bottom to be 5. So thinking in terms of before and after, vertical and horizontal, or other way around, before and after, horizontal and vertical, allows us to do things that are not just multiplication and addition. So here's some DVD bonus material. This is definitely going to get cut and end up on the cutting room floor. I don't edit my videos, everything's the director's cut. But if I look at the graph of, say, if I make my operation, let's say, let's turn cosine off. Well, let's keep cosine on. If I look at the cosine of x and I do this weird operation, I square it. This squaring is happening before the cosine. And we see in the graph a horizontal change. Notice that the amplitude is still 1. The middle is still at 0. However, if I instead I do the squaring afterwards, if I take cosine of x and then square it, now I'm doing the square operation after the trig function, I should see some kind of vertical change. And here comes, slowly they creep across the page. So that blue is the original cosine. And we've seen some kind of vertical change in the green graph. First of all, we notice that the green graph is never negative, because squaring always makes things positive. Squaring negatives makes them positive. So I performed an operation before the trig function and got a horizontal change. I performed an operation after the trig function and got a vertical change. So I really like organizing changes to the graphs of functions this way. Before and after, multiplication and addition. The horizontal and vertical, stretches and shifts. Any questions? Comments? Slide remarks? All right. I've posted homework from chapter 4, sections 1 and 2. Those aren't going to be officially due until the 27th. So you have extra time to work on that. But we need to get started. This is the next thing. This is why we switched to radians. So what you're doing now is you're practicing recognizing your common angles in degrees and radians, the trig value functions, sine and cosine and tangent of those common angles going all the way around the unit circle, knowing that in degrees and radians. And now we're going from going around in circles to stretching out, where our inputs are going out horizontally. So now we're going to start thinking about middle, amplitude, start, and period. That seems like a lot to remember. But that's only because it's a lot to remember, and you have to remember all of it all the time in perfect detail. No problem. Any questions before we adjourn for the week? There's something that I left out. What if the amplitude is negative? So there's a question that I'm not going to be answering today, and I think we just found out what it is. So if you're wondering what happens if the amplitude goes negative, I kept alluding to the fact that it could be negative because on the Desmos, I had my range go all the way down to -4. What happens if we let the amplitude go negative? So find that out and report back on Tuesday. That's going to do it for today. That's going to do it for this week. I'll see y'all on Tuesday. Everybody have a good weekend. Thanks for playing.